Hi everyone, this is Applied Statistics in Healthcare, and this is session 4, the final session of Logistic Regression. And in this session, we're going to look at prognostic or predictive models, and we're going to see how to implement a model, select thresholds, and do a decision analysis. And for this third case study, it's on 30-day diabetes readmissions. And for session 4, again, it's prognostic or predictive modeling. And for predictive modeling, we're going to look at model approximation, selecting a model threshold to implement a model, and a decision curve analysis for clients. Our data is predicting 30-day readmissions for diabetes patients. And this is an example where we have a lot of variables and a lot of data. We initially begin with a model using all predictors, and we can consider it readmission or being readmitted is defined as race, gender, age, weight, and many other variables. And for our final model, using the variable names, it's readmitted.30.days, and we have these fewer predictors. And the HA1C result was used in the initial study, but for this it was not included in the final model because of its low predictive power. And here's some more background on the study. Data was collected between 1998 through 2008. N equals 101,766. There are 50 predictors. We have, for our outcome, 30-day readmission. That overall readmission rate is 0.11 or 11%. The initial study was to predict HA1C and readmissions of diabetes patients. The data includes demographics and pharmacy predictors, and the article for this original study is found in the file section. We have a 30-day readmission that's traditionally a tough outcome to predict because of the numerous causes, and data collection is not available beyond discharge, and it can look very differently between populations. So this is just one outcome that is just a really tough thing to predict. And we see it in hospital systems throughout the country, and it's especially important to note that for that 30-day readmissions, we don't have the information up to that 30 days after their discharge. So there are many things that are that may be missing about a patient's experience that may contribute significantly to a 30-day readmission. This study presents a situation when high predictive validity is not possible. So in other words, this is a tough outcome to predict, and we're going to cover things that we can do to help with that. And we're also going to cover how to implement this into and put it into production. Okay, so in this slide, we're looking at 3 types of models. On the very top, we have a model where it uses all predictors. The C statistic on the top right of that section is 0.650. And that's a moderate level of model performance. The section below that reads as some predictors, and it excludes the pharmacy variables. So again, we see on the far right of that section, the C statistic, or the area under the curve, is 0.646. So there's not a lot of difference between a model with and without the pharmacy information. We would expect the pharmacy information to have more predictive power if we knew the medications that they took, or that they do have a number of medications that could maybe give us a better idea of their health status and their likelihood of being readmitted. And then because of the large sample sizes, models validate at the same level of the area under the curve. So they're not too far off. We do have a lot of data, and so if we did the model validation, they're not going to be too far off. The initial findings we see here are not going to be too far off from the actual model validation. And at the bottom, we do have an approximated model, and you'll notice on the upper right that C statistic is a bit higher, but it's important to note that model performance increased because low sample categories of variables were recorded into larger groups. So there were a few different predictors that had response categories that were small, that had a low N or a low number of responses in that category. So part of the work that I did was I modified some of those variables where I combined them into different categories. In other words, I created the other category. But again, with this, the approximated model validation is not too far off from the initial C or AUC value that we see on the upper right. Okay, and so this graph we're looking at variable importance, and we can see that not all predictors would be considered important, and that's based off their p-values, which you don't want to necessarily limit your assessment to just that. There may be a number of clinically relevant predictors that have higher p-values that may not look significant, but really are important to us getting good results or accurate predictions. But we do see some that do have greater predictive power than other variables. For example, the number of inpatient stays seem to be a good indicator of 30-day readmissions for diabetes patients. And so I did look at a model approximation, even though we do have a really big sample, a large data set with over 100,000 rows of data. So there's we should have, just on that rule of maybe the number of patients with 30-day readmissions divided by 15, that gives you an idea of how many predictors you have. So we have plenty of space. We have a really big sample that would give us the opportunity to use a lot of predictors. We know that we shouldn't necessarily do that based off of that really big sample size. The reason is, if we can think about some examples, we wouldn't expect to see that many causes for readmission. For example, with, say, smoking and lung cancer, we wouldn't expect there to be dozens of causes for lung cancer. There are most likely just a handful of predictors that we could use to predict that. And if we add in too many predictors, if we add in predictors that aren't linked to the outcome, then we can have that. We can have what happened in our last session, where you can have just a lucky split or a lucky combination of predictor values that happen for some of our cases with our readmissions, and then it could end up causing overfitting, and we could have a predictive model that doesn't perform well with future data. So even though we have a really big sample size, we still have a chance for overfitting. And so what a model approximation does is to give us an idea of how many predictors we do or don't need in our model. So from these results, if I use the 0.95 or 95% as my threshold in terms of what I consider an approximate model. So I could see that if we can remove over 20 variables from the model and still have 95% of the predictive power of the full model, which is our gold standard. So we can drop 20 of our predictors that are the least important, and we can still have a very predictive model in comparison to our original model. And just to show you this gray bar between 0.9 and 0.10, the vertical bar, if you go up, you can remove all of these predictors and it will leave you with 95% of your R square in your original model. And that's what we mean by predictive power. Okay, so if I do drop those variables, we're left with our final model. In our final model, we actually have 17 variables. I do adjust for nonlinearity. I add that squared term in there. For example, a value of 10 in the original variable, if we square it in that squared variable, that 10 becomes 100. So I did that for 3 variables, and so we have 17 factors. That leaves us with 20 variables. But if I remove all those variables that we didn't seem to need, we see that our dxy is 0.336. We use this formula to convert that and convert it to the AUC or C statistic of 0.67, and that was very similar. I think it's actually the same level, or it's very close to that 0.676 from our approximated model. So our validated value is very close to our approximated area under the curve. So when we look at the intercept and the slope, we see that they're not too far off. So we have good signs of calibration. We have good signs of discrimination. This is a moderate model. And when I mention good signs of calibration and discrimination, I'm referring to the fact that the validated results are close to the original models, or close to the initial model that we had. So they're not far off. We have a big data set, so we wouldn't expect them to be that far off. Again, we have a moderate performing model. The area under the curve is about 0.67, 0.68. So it's not the best model, but at least it validates well. Okay, so in the final model, we can now re-examine variable importance. And just to note, many variables have categories with a very low n, such as discharge disposition. It is unclear if this has categories that would make the variable look more important than it is, such as a discharge disposition of death, because death would have a 0.0 chance of readmission. It's important to note that area under the curve rewards predicting 0 or no death, as well as 1, which would be death. Oh, I'm sorry. It's a readmission. So AUC rewards predicting 0 for no readmissions, as well as 1, which is readmission. So it's important to note that that the no readmission is part of our calculation, as well as predicting a readmission. So on the most important predictor, it's discharge disposition, followed by number of inpatient stays, medical specialty, number of inpatients squared. We did see some signs of nonlinearity between the number of inpatient stays and the 30-day readmission to help improve the model, we introduce the squared term, which we also call a polynomial term, or just the squared variable. And we can see that there was a benefit in doing that here. It's our fourth most important predictor, so so number of inpatient stays is an important predictor. Okay, now we can put the model into production. We've developed a model that we feel will help meet the level of performance that we would expect with such a tough outcome as 30-day readmissions. We think that model is adequate, so now we want to actually put that model into use. And with logistic regression, you don't get back, it's a probability model, so you get a probability of the outcome, which can go from 0 to 1. Like maybe based on my characteristics, I might have a 50% chance of a readmission. But we don't get back values of 0 or 1 as our output, where it's a probability model, so we get those probabilities instead. So to work with this predictive model, we need to select a threshold or a cutoff to determine when we would consider someone likely to have a readmission versus someone unlikely to have a readmission. From that threshold, we can create that binary outcome that we would have in our real data, in the actual collected data. So what we need to do is set a threshold, and a traditional approach to setting a threshold is using the rate of 30-day readmissions. Here we select a probability of 0.109. With an 11% readmissions rate, if we get down to the to more of a precise value, that's 0.109. So in that case, we would use that as our threshold. Anything above 0.109, when it indicates someone that has an above average chance of a 30-day readmission. Anything below 0.109 would indicate someone who has has a lower than average chance of a 30-day readmission. So we can see that in this upper graph, if we have a blue bar that goes down towards the middle, and that would indicate that threshold, and the green bars would indicate the number, or would indicate how many patients that we predicted to have a readmission had a readmission. And so on this upper part, they indicate all of those patients who did have a readmission, and on this bottom graph, these are the frequencies for patients who did not have a 30-day readmission. So when we set a threshold, we would use it to identify those that would have a readmission, but by setting a threshold, we would naturally have what are called false positives, meaning these are, for example, in the bottom half, these are patients that we predicted would have a 30-day readmission but did not. So with whatever threshold we use, we have the chance for true positives as well as false positives. True positives are what we call what we refer to as sensitivity, and in this second graph, or the bottom half graph, that gray part represents the true negatives. These are the patients we don't think would have a readmission, and they did not, and we refer to that as specificity. And then on the upper gray bars in the top graph, those are false negatives. We predicted that they wouldn't have a 30-day readmission, and they actually did. So we have four sets of values that we can consider when we set a threshold. The area under the curve that takes into account these four different parts gives us an AUC of 0.625. So that's not actually not too bad. The area under the curve of from the model was about 0.67, and so for us to use a prediction as just a single variable, that one variable gives us an AUC of 0.625. So that's actually encouraging to see that the that our area under the curve is not too far off from our regression model. So that's that initial model had 20 variables in it, and that gave us an area under the curve of 0.67. And this one prediction, this one single variable, gives us an area under the curve of 0.625. And then we can see that the strength of the model seems to be is a combination of these false positives and these true positives, the sensitivity. So we see that the proportion of predictions at or above our cutoff is 0.585. So of all these bars, for all the patients who had a readmission, we caught about 59%. So that's not bad. We would like to definitely improve that, but it's not the worst value, and it's also important to consider that predicting 30-day readmissions is a well-known difficult thing to predict. So on the bottom we see that for our false positives, that would be the proportion of predictions at or above the cutoff on the lower graph. That's 0.335. So it's not the we would definitely like to keep that number down, but it's not too bad. It's there is some good and bad with these results, but it's considering it's 30-day readmissions, it's not too bad. And this AUC or C statistic of 0.63, it's not that far off from our validated model of 0.67. So what we can do is consider another threshold. We can also set a more aggressive target. We select a probability of 0.083. That gives us an area under the curve of 0.61, which we see reported on the top portion of the headings for each of these two graphs. And so our AUC went down a little bit. It went down by 0.015 points. It went from 0.625 to 0.61, so it decreased a little bit, but in exchange for setting a more aggressive target, we got that lower AUC actually reveals that our proportion of predictions at or above the cutoff equals 0.803. So we're catching 80% of our patients that had readmissions. So we might ask, well, what would be the cost of getting that improved number of 30-day readmissions? We would see that our proportion in the lower half, the bottom graph, we would see that the proportion of predictions at or above our cutoff is now 0.582. So we are getting more true positives, but we're also getting more false positives. So we need to start thinking about the cost benefit of getting more readmissions, but at the cost of getting more false positives. We have improved our identification of patients that have a readmission, but at the cost of having more false positives. We must consider how much catching a readmission is worth it. So this is when we'd want to talk to our to our clients to ask them what they consider a good cutoff. If we, depending where we set the cutoff, we'll catch more true positives, but we'll also have more false positives. And so this is where a decision curve analysis comes into play. These are considerations in predicting outcomes. We can consider potential benefits. Predictive models and assessment scales can identify those likely or unlikely to have an extended length of stay, fall, 30-day readmissions, and so on. We need to think about the cost of interventions. That's time, money, quality of life, etc. When deciding on using predictions or scales, we must consider how costly interventions are. For example, with a 10% cutoff, it's the same as saying that preventing one readmission is worth the cost of intervening on 9 patients who wouldn't be readmitted. So if we have a 10% cutoff and we have 10 patients to look at, I'll be able to prevent one readmission, but is that worth the cost of whatever it takes to look at the other 9 patients? That might be in terms of staff hours or staff time or staff efforts, but we also need to consider what the effect is on the patient. Is it a big inconvenience? Another example that we can consider would be taking biopsies. For different types of cancers, we might actually need to do surgery to intervene on these patients. So that could be, and sometimes those surgeries have permanent effects. So we need to think about, if I set the cutoff at 10%, what is that worth? So if the physicians consider preventing one readmission is worth the efforts that you make for 9 patients that aren't going to get readmitted, so maybe we might say that there might be 9 unnecessary interventions. If they feel it's that way, then we would set a 10% cutoff. So that's when our clinical stakeholders can really help us figure out what a good cutoff is. And there's an article that's in the files folder, the Vickers 2019, that has more information. And if you'd like to learn more about decision curve analysis, you can click that purple link. And to answer what is a decision curve analysis, it is a decision analysis allows us to determine the optimal cutoff in which we intervene based on our predictive model or assessment scale. For outcomes with high risk to life, we may set a lower cutoff. We may also set low cutoffs if the intervention costs are very minimal. For example, in other words, we compare cost and benefit. So if we have something with has a very high chance of death, we'd probably want to set that cutoff level to a lower value. And if we have something where the intervention itself is cheap, or the expenses are very minimal, then we would probably consider that too. So if the intervention was an auto-generated phone call as a reminder about someone's upcoming doctor's appointment with very minimal cost and very minimal impact on patients, we might consider using a lower cutoff or threshold level. For rare events with expensive interventions, there can be more opportunity for savings by identifying those with low risk, for example, falls, so we can avoid unnecessary interventions. Decision analyses can guide us in how we balance the cost for preventing an outcome compared to the cost of interventions for those who never would have had the outcome. For example, 1 readmission equals 9 non-readmissions. Okay, so here's what a decision curve plot looks like. And so we're looking at what we call net benefit. A net benefit would be the difference between true positives and false positives So if we have a good model that can help identify patients likely to have the outcome, then we should have a good net benefit. And we see that a net benefit of 0.0426 indicates that the difference between our true positives and false positives will be finding about 4 to 5 more true positives per 100 patients using a cutoff of readmissions equal to 0.083. So this is the second cutoff we used in the example above, and by setting that cutoff of 0.083, we get a net benefit of 0.0426. So we would expect to have about 4 to 5 more true positives per 100 patients. So if you have 1,000 patients, that would be between 40 to 50 more true positives than false positives. So it's 4 to 5%. So that would mean that when we go back here, the difference would be you would get 4 to 5 more to the right of that blue threshold than you have false positives. So another way we can think about where to focus our threshold is where are most of these predictions at. So we see that as we get to the upper end or lower end, if we use those as thresholds, there probably won't be a lot of difference in terms of how many more false true positives we have. And we see that we also, going up a couple points wouldn't make a big difference on our false positives as well. It's kind of that middle spot where we have a higher density or higher frequency of our predictions. That's kind of where the sweet spot is in terms of the more we move that threshold, the bigger the impact it's going to have on your true positives and your false positives. So the x-axis in this graph has the percentiles of the predicted scores. And for example, the dashed line ranges from the 5th to 95th percentiles in our predictions or our predicted probabilities. So we would say most of our predictions go from about 0.06 to about 0.26. Okay, so with that cutoff of 0.083, that would give us a net benefit of 0.0426. And I'm going to go to that first red triangle, and that would indicate a cutoff of about 0.083. And we see it crosses right around 0.0426. Okay, and so using a cutoff of 0.109 yields a net benefit of 0.029. So if we go to that second red triangle at the bottom on the x-axis and we go straight up, it's going to be about 0.029, somewhere around there. So we can see that as we move our threshold further to the right, our net benefit goes down. So that's what that dashed line represents. We know that we have our biggest benefit based off of using a lower value. And that makes sense because if we go back up, say this is at the 0.083, we know that we're going to catch more true positives. We're also going to catch more false positives. But at these higher levels, the trade-off between your true positives and your false positives leans more towards catching more true positives. But as we go further to the right, we just don't have a lot more of our of our patients predicted at that level. So there's not, so going from about a 0.18 to 0.22 isn't going to yield the same as going from a 0.083 to a 0.109. But we do see with the 0.109 it yields a net benefit of 0.029. So there is some benefit, but not as much as when we had that more aggressive threshold of 0.083. But it's also important to point out that with our prediction, we can predict those likely to have that 30-day readmission, but we can also predict those unlikely to have that 30-day readmission. So if we have expensive interventions, this is the part that may be helpful for that analysis. So we may say that there's a intervention that costs a lot. So if we can identify those unlikely to have an intervention, then we can say that we don't need to do an intervention on these patients. And by doing so, we should be able to save a lot, and we can also calculate how many patients can we safely exclude from these interventions without raising without raising the number of patients with 30-day readmissions slipping through the net. So these are interventions avoided. We can avoid about 13 of 100 unnecessary interventions with a threshold of 0.083. So that's that first red triangle. If we look up, it goes up to about 13. So for every 100 interventions, we can avoid 13 of 100 unnecessary interventions with a threshold of 0.083. But we can avoid 21 of 100 interventions with a threshold of 0.109. So that second red triangle on the x-axis, if we go up, it crosses around 21 interventions avoided per 100 cases. So that would be the so depending on if we're more focused on preventing 30-day readmissions, or if we're more focused on not intervening when we don't have to, that would give us two different thresholds to consider. 0.083 gives us a greater chance of catching our readmissions, but it doesn't avoid as many unnecessary interventions as that cutoff of 0.109. So we need to weigh the cost benefit of avoiding a readmission versus the cost of the intervention. An automated call may have different considerations than a home care visit. The reason we can avoid more interventions with the higher threshold is that the model has a high specificity level, and the majority of patients won't have a predicted probability over the threshold. Okay, and so in this graph, we're going to look at, it's the same graph that we looked at before, but this plot shows the true positives, which are sensitivity, on the same scale as the bottom graph. So on the top graph, we have those patients who had a 30-day readmission. You can see these bars look a lot smaller, and you see the green and the gray being a lot lower than what we saw in this graph. So in this graph, I have the X scale that same as before, but on the Y scale, which represents the frequency found for these bars. It goes from, on the top graph, it goes from 0 to 1500. On the bottom, it goes from 0 to 30,000. But I made these graphs at a similar height just so that we can easily see the green and the red. But the y-axis, it's a smaller range because there are far fewer patients who had a 30-day readmission than those that did not. So if we go back to that graph again, now they're both on the same scale. The y-axis for both graphs, the top and the bottom, ranges from 0 to 30,000, and so we can see that the number of patients that are going to get readmitted is a much smaller number. So this plot shows the true positives on the same scale, so we can see exactly how many patients we're working with. We can see there are far more patients that don't have a readmission. So this big proportion that are true negatives, that can give us a good way to improve uses of our resources. Okay, so that's it. In this last session, we looked at different ways of implementing a model. We thought about setting different thresholds. We initially went with the prevalence rate. For this sample was 0.109. That's a traditional approach. It's not the best approach because there are a lot of different things we need to take into consideration, such as the cost and benefit. So we adjusted our threshold. We made a more aggressive threshold. We're able to catch more readmissions, but at the cost of having more false positives. So if we intervene on all patients, then that's something we should probably consider. But in general, a lower, depending where the majority of predictions are at. In this part, we can kind of see where these bars are at their highest in the middle values. But it is both of these distributions are skewed. We would know that moving this blue threshold, this blue vertical bar, moving the threshold in those sections would have the biggest impact on what we would call our net benefit. And so we reviewed a decision curve analysis that gave us ways of showing the net benefit and of our model, using our model. And when we review this with our stakeholders or our clients, they can help us identify, for example, how many non-readmissions is worth catching one readmission. And from that value of, if we say one readmission is worth 9 non-readmissions, that gives us a probability level of 0.10. So if they tell us that, we can easily convert that number into a threshold and set our and implement our predictive model that way. We can also look at interventions avoided. So we can see what the cost, because we're doing a cost benefit, we have that information on interventions avoided as well. And that's it. Thank you.